I was suggesting that we all watch the code show stream together. So that will take care of the conflict.
Yeah, we are live. We can start.
All right, thank you. Yeah, okay. So I think, it appears that we are live at the moment. Those of you who are watching on YouTube, welcome to the session. You're also welcome to join us on Zoom. If you're on Discord or if you're on the mailing list, you already have the link from the announcement. So you're very welcome to join us directly on Zoom. That way you can have a two-way conversation with us. But if you prefer to just watch the stream, by all means, please drop your comments in the chat. All right, so a very good evening, especially to everybody who has joined us on Zoom. So please let us know if you have any specific questions that you would like us to address in the stream. But otherwise, we have our standard ritual of Arjun helping us with his programming assignments. So we could default to starting off with that. So while we are waiting for other questions to come in. So Arjun, would you like to maybe do a quick overview of the programming assignments for this week? I think the deadline is tomorrow, so this may be some timely advice from you for how they might want to go about it. So,
sure. Yeah. So the due assignment is week 5, right? Week 5 assignment 1 and 2. I think they're both due tomorrow. So let's just go over the problems. The first problem, I'll also need to recap my memory, so I'll just read the problem. You're given a rooted tree containing n nodes, which are numbered from 1 to n. Each node has a weight attached to it, given by wi, and your goal is to find a pair of nodes u, v, such that u is an ancestor of v, and weight of u minus weight of v is maximized. Right. So, okay. So before that, maybe a larger context is that week 5 is based on graph traversal. So in particular, it's BFS and DFS. And I think one simplest hint I can give is that problem 1 is DFS, and if I remember right, problem 2 is BFS based. So in this particular problem, you're given a tree, and in particular, you're given a rooted tree. The nodes are numbered from 1 to n. The node. Okay, so I think I probably missed mentioning that the root is node 1. I'm sorry, I seem to have missed that in the statement. I think many of you just... Oh, no, sorry. My bad. Node 1 is not the root. It's given in the input statement. It's given in the input constraints. Yeah, so you're given a rooted tree, and you want to find a pair of vertices such that one is the ancestor of another, so that it's like something and something under its subtree. You want v to be there, u to be at the top, and you want the weight attached at u minus the weight attached at v to be as large as possible, right? So in particular, there can be many such pairs, right? So say you take just say you take the graph to be a path. That is, say it's node 1, node 1's child is node 2, node 2's child is node 3, all the way down up till node n. So in this case, how many different pairs of u, v are possible? Can anyone tell me this? Okay, I'm not sure. So sure, Neeldhara, I think it's fine to make this slightly interactive, right?
Yeah, absolutely.
Yeah. So if anyone is interested, can you maybe first think of the number of valid pairs of nodes u, v such that u is an ancestor of v in this particular tree that I mentioned, where the tree is a path. That is, node 1 is the root, then it's node 2 as it's a single child. Node 2 has a single child, which is node 3, all the way up till node n. Right? In this, how many different valid pairs are there of u, v? So you see that 1, 2 is a valid pair because 1 is an ancestor of 2. 1, 3 is a valid pair. 1, 4 is a valid pair, all the way up till 1, n. Similarly, 2, 3 is a valid pair, but 2, 1 is not a valid pair, right? Because 2 is not an ancestor of 1. So 2, 3, 2, 4, all the way up till this, and so on and so forth. So for every I comma I plus 1, I comma I plus 2, all the way up to I comma n will be valid pairs. And then I think if you sum this up, I think for n minus 1, it's going to be 1. For n minus 2, it's going to be 2. All the way up till for 1, it's going to be n minus 1. So the number of valid pairs is going to be 1 plus 2 plus 3 up till n minus 1, which is n minus 1 and n by 2. Right? But this is irrelevant to the problem. Just wanted to give you an idea of what we are looking at. Right? Okay. Yeah. So the first naive approach that we think of is to basically look at all such pairs and find the max and find WU minus WV for all such pairs and take the maximum. But then this exercise that we did just now tells us that this is going to take a lot of time, right? Because, okay, sorry, 1 second.
Okay, so I guess while let me just sneak in a quick comment. Those of you who have joined us on Zoom, can you give us a quick +1 in the chat if like the naive approach made sense to you, or if you need a clarification, then you could just request it. But could you please post a +1 if it made sense? Okay, thanks, Bhupati. Anybody else? Okay, so I think we have a thumbs up reaction as well from Shubhajoy. Thank you. Govind Kumar Jha, thanks. Thanks for letting us know. Anyone else?
Yeah, sorry, I'm back.
Sure,
There's an issue with the lockout, which I had to, which I messed up.
Yeah. Oh, okay. What? Right, okay. No, I was just requesting everyone to give us a +1 in the chat if
right.
the naive approach that made sense to them. And if there's a question about anything that wasn't clear, then please do post it as well. So I think we have an indication from about a few people saying that it's making sense so far.
Correct. Okay. So coming back, so the naive algo we saw is going to take at least n square time, right? Because we saw that the number of valid pairs that we saw in this example, in this one particular tree itself is n minus 1 into n by 2, which is of the order n square, right? So typically, so even though in this problem, the subtask, the constraints I've given are such that n is less than or equal to 10 power 4, what I would ideally want is an is a solution better than n square. So here n square is like 10 power 8, which might or might not pass. To be very frank, I do not know if it passes. I'm hoping it doesn't pass. But the point is, we were not able to upload a larger test file, so we just capped it at 10 power 4. But this is a problem which is supposed to be solved for something like 10 power 5. So even if you have an n square solution, I would highly recommend that you try and solve this in better than order n square. In particular, you should try and solve this in order n time, okay, and not order n square. So the naive solution, whatever the solution might be, right? So we don't know how to look at the pairs. Any solution which goes through that approach of looking at every valid pair and taking the maximum of WU minus WV from amongst them is bound to take at least order n square, simply because of the example that we saw. There might be other graphs which have even more. That's actually not the case, but we don't know that, right? It might be there, but what we know for sure is that there is at least one graph, one family of graphs in which this approach is going to take at least order n square time, right? And that's kind of bad for us. So what does this lead us to? This basically gives us the first kind of, not an observation, first say train of thought, which is that we should be looking for an approach which does not look at every pair of valid things and then takes the maximum. We should try to kind of combine things together and then get the answer from a combination of valid pairs at one go. And this is typically where dynamic programming comes into picture. Something like a dynamic programming aspect is typically used when we have this kind of thought process that we follow. And here, I mean, you could say it's DP, you could say it's just DFS, but this is where we get to. So now let's look at we'll try to kind of coalesce a lot of different pairs in one shot. Okay, so for that, one of the first things we can do in such a problem is fix one of u and v. Right. So here we're looking at a pair of nodes u comma v. What we can do is, okay, if u is going to be node 5, what all can v be? And amongst all of them, can I maximize my wu minus wv, right? Or the other way is, if I fix v to be node, I don't know, 7, what all can u be? And can I find the maximum wu minus wv in this case? These are, I think, two natural approaches which you should think of whenever you have pairs. One way to easily, so you want to look at all pairs. We already saw that I can't afford to look at all pairs. So two natural ways to go about is, okay, I can't look at all pairs, but let me look at all pairs which have u to be 1. Then I look at all pairs which have u to be 2. Then I look at all pairs which have u equal to 3, right? And so on and so forth. And if each of them I can do it very fast, say in order 1, right? Then in order n, I can look at all of these. Or if this doesn't work, the other approach is to fix v. If v is node 1, what is the best I can do? If I can find this in order 1, then I'll go to v equal to 2. Find this in order 1, and so on and so forth. And then I'm going to take the max amongst all of these. And then again, I'm going to get an order n approach, right? But I don't want to tell you which of these two approaches is going to work. So think about this, right? So I think this is a very relevant, it should hopefully be a pretty helpful clue. So there it is. This is the clue. So sorry, not clue, hint. Try to fix one of these two nodes and find out the best you can do for the other node, the other variable node. We want to maximize this, and this I want to kind of find very quickly, right? So try to think of this in such terms. In particular, the first question you should ask is, okay, if I fix u, what are the values of v, right? Similarly, in the other approach, if I fix v, what are the values of u I need to look at, right? And then amongst them, should I pick the maximum wu, or should I pick the minimum wu, or should I pick the maximum wv, or should I pick the minimum wv, something of that kind, right? So think along these lines, and I think that should hopefully lead you to a solution, which then you can implement using DFS, right? So at the beginning, don't think about DFS. Think of just solving this problem in terms of pairs and so on, of course, with a tree structure. And you'll see that when you do it using DFS, each of these can be done in like kind of like constant time, right? That's where the whole trick comes into the picture. Okay, so I don't want to say more about this problem. So, but if you have any concrete questions, please ask me before I move on to the next question.
Yeah, for anybody watching on YouTube, you could just post the questions in the chat if you have any.
Okay. Yeah, okay. Shobhaja, you tried BFS, but that was my first hint. I mean, okay, BFS is going to be pretty complicated for this problem. So my suggestion is do DFS. So if you try BFS and don't get it, then the next step is just try DFS, right?
I should say that I think somewhere in the lectures, so for week 5, I think most of the problems that were chosen for the lectures were such that you could do either BFS or DFS. I think I wanted to illustrate that point partially, that many times what you can do with BFS, you can also do with DFS and the other way around. And I think I mentioned in passing that this is not always the case, that for some problems, one approach is much more naturally suitable than the other one. And I don't even think there is a formal way of saying that the traversals are equivalent. They certainly are not. So I should have probably emphasized that a little bit more. So
Okay.
the assignments are a way to drill this down, I guess. So yeah, I mean, so please don't go only by the examples in the lectures. So there, I think I just wanted to make sure that you have enough practice doing both. But I did say practice both because you might need either one. So sorry if that was a bit misleading, folks. So please pay attention to these hints. I think they're useful. Thanks, Arjun.
Yeah, Shubhajoy, I think you should just try BFS, and that should make life a lot easier than BFS, at least in this problem. I think there can be a solution using BFS, but it's going to be pretty non-trivial as compared to DFS. Yeah. Cool. So let me just look at YouTube. Okay. I solved it in order n square, but doesn't get how to solve it in order n. Okay. Shad, so hopefully the hints I gave, the hints I gave are for order n. So try thinking along those lines. And if you don't get it, we will obviously discuss it next weekend as well in more detail. Yeah. I don't want to go into more detail on how to get it to order n. So the approach for order n square and the approach for order n are similar to the first step, but then there is a lot more involved about the fixing one and looking at the other as a variable kind of approach. Yeah. Cool. So let me move on to problem 2. Okay. Oh, so this was the coins. Yeah. So I looked at it only like half an hour back. So in this problem, you're given an n cross m grid. Some of these grids are empty. Some of these grids are blocked out, right? So blocked out as in they're inaccessible. They're like not in the picture at all. And you have two integers r1 and r2 for radius 1 and radius 2. And you're given two coins, A and B. Coin A is initially in 1, 1, which is say the top left corner, and coin B is in 1, n, which is in the top right corner, right? And in each turn, you first pick coin A, and if it's currently in the cell x1, y1, you can move it to another cell x2, y2, which is not blocked, such that the Manhattan distance between these two cells is at most r1, right? So what is Manhattan distance? Manhattan distance is also called taxi cab distance. It is basically if I move only in like axis parallel, like from every node, I can go up, down, left, or right? These are the only directions I'm allowed to move in. So then what is the minimum distance? What is the minimum number of cells I need to traverse before I get to x2, y2? That is called the Manhattan distance between n two cells. So if the Manhattan distance is less than equal to r1, then you're allowed to go to x2, y2. Then you go to coin B, and similarly for coin B as well, you start from say x3, y3, and then you can go to x4, y4, such that the Manhattan distance is at most r2, right? So this is what you're allowed to do, and your objective is to ensure that both A and B end up at the same cell, right? And you want to find the minimum number of turns needed to do this. So is the problem clear? Okay. Just give me 1 second. Yeah, okay. So this is basically more of a BFS problem rather than a DFS problem, because you have these concept of radius, and radius, I think the first thing you think of is BFS, because in BFS, what do? You you from a given vertex, you explore all the vertices which are at distance 1 from you, then which are at distance 2 from you, and so on and so forth, right? So here in this problem, it's like you want to explore all cells which are at distance less equal R1 from you. And similarly for the other coin, you want to look at all cells which are at distance less equal R2 from you, right? And you want to kind of keep doing this alternatively, such that you end up with a cell which is common in both these BFS trees, right? So I've kind of given a very, very huge hint here. So just to try along these lines. So it is BFS, but it's not your typical BFS where you do one level each. So instead of one level each, here you do R1 levels, and then in this side you do R2 levels, right? So I hope that kind of makes sense. So you're basically looking at all the cells from which coin A can go to, similarly all the cells which coin B can go to, and you keep doing this until you reach a point where there is a cell which both of them can reach, or you reach a position where you kind of finished your traversal and there is still no cell which is common between both the kind of reachability tree of both the vertices, right? So that's where you kind of give up and say, okay, this is not possible. So the answer is -1, right? I was trying to think of a way to give a partial hint, but I wasn't sure what exactly to give. But yeah, so hopefully this should be helpful enough. So the major point is this: it's BFS with the single main modification, which is that don't look at it one step at a time. Instead, look at it R1 steps, and in the other BFS you do R2 steps, right? So think along these lines, and hopefully that should help. Any specific questions?
So Arjun, did this problem have subtasks?
Good question. Let me check. Yes, there are subtasks. Okay. Oh, the subtask is R1 equal to R2 equal to 1, which kind of boils down to your typical BFS.
Right.
Right. Thanks. Yeah.
So I'm just curious, for those of you who are attending, did anyone finish this regular BFS subtask? I mean, if you could give us some indication, mention it in the chat or raise your hand or something. Also, by the way, I mean, we don't really have any serious protocol here. Since we are a small group of people, please feel free to unmute yourself. And, if you just find it easier to speak up to discuss, feel free to do that. You might just need to know that we are, this is a recorded meeting. So that's the only thing, but please feel free to pitch in.
Yeah. So Shah Dalam has a question. I have one confusion. If we aren't able to move any one of the coins, but the other coin can be reached, then what should you do? So Shad, if you notice, the problem says the Manhattan distance should be less than or equal to R1. So in particular, in a turn, you can just decide to stay in the same cell that you are in. Even if you're not able to move anywhere, even if you stay at the same cell, it's a valid move, right? Because it doesn't say the Manhattan distance should be equal to R1. It should be less than or equal to R1. So 0 is less than or equal to R1. So if I just stay in the same cell, the Manhattan distance I've covered is x1 minus x1 mod plus y1 minus y1 mod, which is 0 plus 0, which is 0, right? So staying in the same cell is a valid move. So that is something you can do, right? So does that answer your question? So it's totally possible that you don't move one coin, but you move the other coin. Okay, that'll be a lag because it's on YouTube. But yes, okay, hopefully that should answer the question. Can implement backtracking to check for all? Not really, Shubjoy. So in this case, backtracking will, okay, so typically backtracking is kind of an exponential solution almost always, because at each point, the number of, okay, think of it this way. suppose there are no blocked cells at all in the entire grid. Okay. And forget the second coin. Say you're only looking at the first coin. And say you want to reach 1, n, or say n, n. So when you do backtracking, it is going to take time proportional to, say, the number of paths which are possible to go from 1, 1 to n, n, right? That's approximately the amount of time that you'll spend, depending on how you exactly implement backtracking and so on. But it's going to be something along those lines. And you can easily see that this is a very large value, in particular for an n cross m grid. If you also put the extra condition that you can only go right and only go down, the number of paths is like n plus m choose n, or plus 1 minus 1. I don't remember exactly. It's going to be of the order of n plus m choose m, which is like n power n minus n. Like it's exponential, right? So that's not something which is typically possible for larger grids. So backtracking is typically something which we follow only for very small. So I say like 8 cross 8 or like 10 cross 10. Even 10 cross 10, usually these things start failing, unless you have some very, very rigorous pruning techniques. But yeah, typically backtracking, you go for only very small grids. Even for 100 cross 100, even for 10 cross 10, it's typically not feasible. That's correct, Shad. Exactly. No, backtracking is not exactly BFS. So BFS is a much more structured traversal where you only look at each cell once, right? So BFS is more like traversing the cells, whereas backtracking is looking at different paths. So in backtracking, you look at the kind of the main basic unit you're working with is a path, whereas in BFS and DFS, the basic unit you're working with is cells. So if a cell has already been visited in BFS and DFS, you wouldn't visit it again. Whereas in backtracking, you might visit the same cell multiple times, right? So, or maybe the backtracking you're thinking of is slightly different, in which case it might be actually BFS, which you're calling backtracking. But in general parlance, I would not call BFS as backtracking. Okay. In week 4, program 2, approach was okay, 1 second. Okay. Let's make it free time. DSU. Okay. So in week 4 programming 2, program assignment 2, we had a graph with n vertices, m edges, and each vertex had a weight associated with it. And we were asked to do Q updates, where type 1 update was deleting an edge, and type 2 was updating a weight of a vertex to something else. And what we wanted was the maximum weight amongst all connected components after each of these Q updates. So, so what Dr. Durga is proposing is to have a new DSU after removing each edge. So, ma'am, maybe you can consider it like this. Say I have 4 vertices, A, B, C, D, and say the edges are, say it's a complete graph, like all the possible edges are present. So currently, so I'm assuming you're going to create one DSU where all these edges are added to it. So you just have like one connected component in some sense. And now after deleting each edge, at some point, you're going to end up having multiple connected components and not just one connected component. So how exactly do you figure out when this happens? because removing elements from a set is not supported by DSU. DSU typically supports only inserting elements, right? So I think that is where the main issue lies. And the main trick in this problem was to actually look at the queries in reverse order. That is the Q queries, like you have query 1, query 2 up till query Q. What you're expected to do is look at query Q first, and then query Q minus 1, and then query Q minus 2, and so on. Like basically chronologically, you look at it in reverse order. Okay. So now what happens is deleting of edges becomes addition of edges. It becomes insertion of edges, right? So say my fifth query was to say I have total of 10 queries, and going from query 1 to query 10, at the fifth query, I'm deleting an edge, say u comma v. But then now when I'm looking at the same thing in reverse order, that is, I'm looking at query 10, then query 9, then query 5, so query 8, 7, 6, 5. Now when I come to query 5, the query was actually to delete. But now because I'm looking at it in the reverse order, what in the forward direction was deleting now becomes adding, right? So my query 5, instead of deleting u comma v, becomes inserting u comma v, right? And now my DSU, my typical normal DSU, supports this. So that is what makes life very easy in the second problem, which is the one single trick is to look at all the queries in reverse chronological order. So all the deletes now become inserts, which is something which our DSU can handle. And after and whenever you have updates, you just update the weight, and to output the weight of any connected component, you just have all the connected components. So you maintain, say, a heap where you maintain the maximum, you maintain the weight of all connected components. And when you merge two connected components, you have to delete the old connected components and then insert the new connected components weight. And because it's a heap, you'll get the maximum value each time in constant time, so that you can get the answer in constant time as well. Right? But I mean, by answer, I mean the weight of the maximum connected component, you can get it in constant time. Does that kind of make sense? If q of 0 equal to 1, e dot remove of h. Sorry, so what is q of 0? Is it checking whether the first query is of type 1? Okay. Okay. I think I understand what you're doing. Okay, so you're basically So what you're doing is going to end up being a order n into q solutions. Okay, if I understand correctly, what you're doing is each time you're looking at the queries in the normal order, and each time you're just removing edges from the edges list, and you're just building an entirely new DSU from scratch, right? Okay. So that is basically something which you should have gotten it correct for subtask 1, right? You should have gotten 30 points. Did you get that 30 points? And for the larger thing, okay. And for the larger thing, you would have gotten a time limit exceeded, right? Okay. So okay. Sorry, I had misunderstood what you were saying at first. So what you're doing is correct. There's nothing wrong in what you're doing, except that it's going to take a lot of time. And why is that? Let's analyze the complexity of this algo. There are queue updates, and each time removing an edge is constant time. That's fine. Clearing is also fine. But when you're building the DSU, how much time do you spend? You spend time proportional to the number of edges which exist, right? Because fourth problem, I think you mean fourth test file. Okay. Wrong answer is, I'm not sure why it's wrong answer, but it'll definitely time limit exceed if not wrong answer. Wrong answer, maybe there is some, then there is probably some bug as well in the code, which maybe your array size is not large enough. But I'm sure that even if the fourth file gets wrong, the correct answer, then it should. Okay, again, I'm not sure about the exact large test file which I uploaded. Ideally, this solution should get a time limit exit. Let me put it that way. Even if somehow you got it accepted, this is not the intended solution, because the time complexity is much larger. So let's analyze the time complexity. So as I said, you are doing few different updates, and in each update you're building a DSU from scratch. And how much time does it take to build a DSU? It is order m into log n, or the reverse Ackermann function. Let's just take whatever it is. Let's ignore it. It's at least order m time, right? Because you have to look at all the edges and you have to add it to the DSU. And you can have your queries such that, say, none of the edges are removed, right? So in which case the number of edges in each query is going to be order m itself, right? So total number of operations you do is at least order q into m, but q is 10 power. Oh, okay. So q is 10 power 3, m is 10 power 3. So again, so I can kind of keep coming back to the same points. So the constraints that we give in these problems are actually much lesser than what we want to give, mainly because it's uploading large test data on these platforms is hard, or it kind of doesn't support. So if you do have an order q into m solution, it might work, but that is not what is expected. What is expected is more along the lines of q log n plus m log n. Okay. So in this particular problem, will the solution work? Yes, the solution should work. You will actually get 70%, so 100% itself with this thing, but I think you just have a bug in your code somewhere. But I would strongly suggest that you try to think of a solution which is better than order q into m, which is in particular order q log n plus m, q log n plus m log m, and m log n, something along those lines, right? Which is where the whole trick of looking at it in reverse and using DSU carefully comes into the picture. I should start sending announcements with each problem and say, okay, this expected is this, but you'll probably get it right with even a suboptimal solution, but try to do something better as well. I've been ignoring to do that. Yeah. Great.
Sure, that's fine. I mean, yeah, it would probably be. Yeah, I mean, I think that would be useful.
Yes, definitely. Yeah.
Right. Yeah, I think it's. But like a couple of follow-up comments on YouTube. Sorry, and perhaps you've taken them already, but.
Okay. No, I actually didn't look at them. Can you please discuss the problems after deadlines? It says. Definitely, sure. Yeah, we'll definitely discuss week 5 order and approach. Week 4 problem 2 constraint is a bit low. Correct. Okay. Yeah. So Shahid, I think that's exactly what I was talking about right now. Thanks for bringing this up. Yes, exactly. You're absolutely right. N into Q sadly will pass in this problem, but that's not expected to pass. So I would strongly recommend that you try a solution which is much faster. So assume that N and Q are 10 power 5 instead of 10 power 3, and try to get a solution which works for 10 power 5, N, M, and Q being 10 power 5 instead of 10 power 3, right? So think along those lines as well.
Nice. So I guess would be fair to say that we have discussed both of the problems for the currently ongoing assignment. If there are any more questions about the BFS, DFS programming assignments, this would be a good time to post them so that we don't miss out. Okay, I think, okay, there's another follow-up comment perhaps. What about the larger constraint for week 4, Arjun? Do you want to address this now?
Can you please discuss that larger constraints week 4? Yeah, sure, that's exactly okay. So maybe I'll go in a bit more depth on that. So the trick is basically to look at the queries in reverse order, right? So instead of looking at it as query 1, query 2, suppose there are 5 queries, query 1, query 2, query 3, query 4, query 5. Think of it as first doing query 5, then query 4, then query 3, then query 2, then query 1. Okay. So the first thing you should notice is what is the graph I start with, right? So initially I have some initial graph. Then I have query 1, query 2, query 3, query 4, query 5, and some of these edges are deleted, right? So what I have at the end of query 5 is a graph with some of the edges deleted, right? And I can just look at the queries from left to right once and see which all edges have to be deleted, and I'll get my final graph, right? So now I have the graph which is after query 5. Great. Now I'm going to look at my queries in reverse chronological order, right? So I'm going to look at query 5, then query 4, then query 2, sorry, query 3, query 2, query 1. So if query 5 was a delete query, right? So it said I want to delete u comma v. Now, when I'm looking at it reverse chronologically, that delete instead becomes a insert, right? So just kind of play it in your head, right? If you're going in forward motion, an edge is deleted, but now when you reverse time and go backwards in time, that is inserting an edge, right? So if I have a graph, 1, 2 was deleted in 1 second, and I go, when I'm going in the reverse direction, earlier 1, 2 was not there, but now 1, 2 is there, right? So it's like inserting 1, 2, right? So all delete queries now become insert queries, right? And why is this good? This is good because our DSU are very, very efficient. We've spent a lot of time making our DSUs very efficient, right? We have multiple different algos to do it, data structures to do it, various heuristics and so on. So DSU is something which we're very good at, but DSU can handle only inserts, right? And that is what we're trying to do here. The whole point of this problem is to convert the queries such that they're not deletes anymore. Instead, they're edge insertions, right? And once you've made this, the next query should not be very hard. So what is the other query? The other type of query is changing my weights, right? So say my query 4 was changing a weight. Say I wanted to change the weight of node 8 to, node 8 was, I don't know, 100. I want to change it to 200, right? Now when I'm coming from reverse direction, it is changing it from 200 to 100, right? So how do you keep track of this? So one thing to do is, when I'm looking at the edge, I'm looking at the graph which exists after Q5, not only do I need to know which all edges are there, I should also know what are the weights, right? So I'll just go from left. I start out with my initial weights. I go from left to right. I apply all the changes to the weights. It's just an array, right? Weights are just in an array. I have a W array, W1 to Wn, and I have my initial W array. Then when I go from query 1, query 2 to query 5, if say query 4 was changing 8th node from 100 to 200, I go to W8 and change it to 200. Great. I do this for all the type 2 queries from left to right. I finish it. So now what the array at the end of Q5 has is the array is the weights of the graph at the end of time, right? Now I have that. Now, when I go back, when I go back in time, right? I go reverse order in time. Now, when I come to Q4, the changing of 100 to 200 is now 200 to 100, right? So when you look at W8, it'll be 200, it won't be 100. So this 200, I now have to change it to 100, right? So 200 I know, but how do I know what I should change it to? The fact that I should change it to 100, how do I keep track of this, right? So this is a slightly interesting question. So think about this a bit, right? So a simple hint is just that for each node, just keep track of all the weight changes that are happening. I mean, for node 8, maybe initially its weight was 5, then it became 100, then it became 200, then it became, I don't know, 85, and so on. So I can keep this as a vector or a linked list or whatever you want to do, right? And then, so now when I'm coming in reverse order, so it's just going through this linked list or vector in reverse order. So the last number will be 200. But now when I get a Q4, which is to change the weight of node 8, I just look at the element before it, which is 100, right? So then I know that the change in the weight is from 200 to 100, right? So then I'll just go to my weight array and put 100 there, right? So this is the way you reverse the type 2 queries. Does that make sense? So we've seen how to reverse type 1 queries, which make edge deletions into edge insertions. And we've also seen how to reverse type 2 queries, which are weight updations. And now the thing that we need to output is at the end of each query, we want the maximum connected component, right? And this is our usual stuff. So we have a DSU. So for each component, I can maintain its weight. I can maintain this weight in a heap. And I just take the max in that and I output each time, which should get me my final answer. Does that make sense?
So you're waiting for a response in the YouTube stream, Kim?
Yeah. I think there's a significant lag, but okay. I think we can assume that's kind of resolved. Any other questions? Thanks, Raviraj. I'm glad you find them helpful.
Yep. Thank you, Raviraj. So we are almost on the hour. I suppose started a few minutes late, so we're happy to hang out for a bit longer as well. If there are any questions, please let us know. In the meantime, let me just make a bit of an announcement for those of you who are tuned in. First of all, I'm sorry for the delay that we have experienced with week 6. This was mostly thanks to a technical issue at my end, because of which I couldn't upload the materials around the usual time. So what we are going to do is share with you materials for week 6 and week 7 with a combined deadline. And I think it works well also because it's sort of a combined theme. I think weeks 6 and 7 look at shortest paths and spanning trees, which are kind of related ideas. And once again, for the next 2 weeks, we will be looking at flows. We'll build up a little bit of theory first and then look at several applications. So the next 2 weeks, which is to say weeks 8 and 9, are also sort of joined by a common theme. So yeah, I think you should have access to the materials by tomorrow for both the weeks, and both the lecture materials and hopefully also the assignments. So that's the timeline at the moment. And I'd also like to share that we are again tentatively planning to have an informal contest. It will not be a graded assessment or anything, but we are hoping that you'd all enjoy participating nonetheless. So this contest will be hosted on CodeChef, and we're still trying to finalize the logistics in terms of the exact date and time and so on. But I just wanted to tease it a little bit, and hopefully that's something that you look forward to. And we will have more details on that front very soon. And the questions will be based on everything that you have learned in the course so far. So I think that should be fun. And again, if you have any suggestions about any aspect of the course, please keep them coming. And you all know that we are generally around in Discord as well as the mailing list. So in case you didn't have a chance to ask your question now, or if you're watching the recording and you missed the live session, please feel free to connect with us there until we meet next week. So yeah, so all right, so there's a suggestion from Shad. I think that's a good suggestion. From next time, I think from next time we will probably, when either of us are talking through one of the problem solutions, I think Arjun, we can probably make it more of a whiteboard kind of session that should be workable.
Yes, yeah.
Great. All right. So yeah, so question about whether it'll be a rated contest on CodeChef. I think unfortunately that's unlikely at the moment. We're still working through the details, but we'll let you know. We understand that it would be more interesting if it was rated, but we are trying to make up for that with other kinds of incentives. But we'll see. I mean, as I said, we're still hashing out a few of the details, and we'll let you know. Yeah. So yeah, thanks for that question. Is there anything else? Okay, so if there are no further questions at the moment, as I said, we will, we will be sure to catch up with you on all the other forums until we meet you next time. And I'm not sure if, Arjun, you might have to get to the CodeChef lockout after party or something. So
No.
so yeah, I think so for those of you who had to make a choice, sorry about that. I think we will try to sanity check the timings of the live streams going forward. Right, so Shadia, you're not okay. You're curious about the contest. Yeah, we'll definitely get back to you with more details on that. This was, I think, I just mentioned it so that we also get to work and get it ready for you all pretty soon. And yeah, we'll definitely give you a heads up. I'm not sure if your suggestion for 1 week was for the assignments or for the contest. We'll definitely give you an advance heads up on the contest, and for the assignments as well. You'll definitely have at least a week to go through them. So we'll ensure that. Yeah. So once again, thanks very much everybody for joining, and look forward to seeing you soon once again. Really appreciate your stopping by on a Saturday evening. So for now, let's call it a day here, and I think we could wrap up the live stream. And this have been taking away all the limelight, Arjun. So which is awesome. All right. So, okay. So I think thanks very much once again to everyone who is here with us on Zoom. I really appreciate your stopping by. And so I guess goodbye for now, and we'll see you next week. And Arjun, maybe I'll catch up with you offline about some logistics.
Sure. Okay.